Okay, this is going to be a review of what you need to know for the final. More conceptual, less. What's the word that I want? Less analytical, like calculations, etc. This is more conceptual. Where does a Newton come from? Where does a Pascal come from? What is the atmospheric pressure? Where does that? What actually is it? Give me a concrete example of atmospheric pressure. That's what I'm going to do right now. Clear? Okay. Pressure in a fluid. We're going to talk about that. We're going to talk about changes of density as I submerge something in fluid. Clear? Okay. This is a box. This box is a cube. It's 1 cubic meter. It's 1 meter on each side. Clear? So far, so good. This box sits on the ground and forms an area of 1 square meter. Is there anybody who doesn't get that? Easy? All right, now, let's look at the density of water. The density of water, as you know, from this year or years before, density of water is 1 gram per milliliter. Make sense? You remember that? Yes or no? If it's 1 gram per milliliter, what that means is 1 gram equals 1 milliliter. They're equivalent. Yes or no? So if I have a liter, which is 1,000 milliliters, that has a volume of 1,000 milliliters. Therefore, it has a mass of 1,000 grams. Are you all right with that? It's all on the board. So 1 liter is 1 kilogram. Yes? Yes or no? Yes. This box, in terms of water, will fit 1,000 liters. Therefore, it's going to fit 1,000 kilograms. Are you all right with that? If you were sitting under that box, that's a metric ton. That's 2,200 pounds for the Americans and the British in the audience. Very heavy, isn't it? Very heavy. Can you imagine being under that box? Would you be crushed, yes or no? Yeah. You would be crushed. You wouldn't be able to breathe. You would be crushed. I could hear the bones snapping now. What is that crackling sound? That's his bones because he's under that box. Rigid container. Clear? Okay, now. Let's find out. That's the mass of that box, 1,000 kilograms, correct? All right, now I'm going to erase things that are on the board that we've already used, okay? We've used this. That's how we came. We used this. We used that, okay? Now, I know that weight, Fw, according to Newton's second law, let's not even say Fw, is mass times acceleration. That's what weight is. I'm sorry, that's what force is. Yes? That's what force is. I take a mass and I accelerate it. I do that with a force. Think of it this way. You ready? You're in a food store. You're in Lulu's. And your basket is full of food. Can everybody picture that? Raise your hand if you can picture that. All right, now it's stopped. It's not moving. There's a lot of mass there, isn't there? A lot of inertia, right? Aiden, you're all right with this? I'm not asking you to reproduce this. I'm simply giving you the underpinnings of what you do have to know so that what you do have to know makes a little bit more sense. That's all I'm doing. You get it. Have you ever been in a store to buy food, or are you an android that simply needs to be oiled periodically? Or you have food. Okay, next. So you have this enormous cart that you have to push, correct? In order for that cart to push, don't you have to apply a force? Yes or no? Now, that cart is going to do what? It's going to start moving. Yes? You're going to eventually get it to a velocity that you're in a hurry. So you're going to be going very fast down the aisle. I hope you don't hit anybody. But in order to go from 0 to that steady velocity, don't you have to accelerate? You have to accelerate the cart from 0 to some constant velocity, yes or no? Okay. What you used to accelerate that mass was a force. Let's get a little bit more complicated. If I'm at a constant velocity, do I need a force to keep myself at that constant velocity if there's no friction involved ever? No, you don't. Because once you get it to that constant velocity, it's going to move. Because the only reason it changes velocity is because you applied a force. That's why something accelerates. You applied a force. That's Newton's second law. Now, you know as well as I do, T, you're following everything I'm saying. I feel like I'm selling rain. I feel like the rainmaker. I feel like I'm like doing some show here. Okay? You know as well as I do that when you push that cart and you get going at a comfortable speed, you are applying a force, but it's much less than the force that you originally applied to that cart that was stationary. Do you agree? Yeah. So what force are you applying there for? Are you applying a force to move that enormous cart full of all kinds of things? No, you're not. The only force that you're applying, T, listen carefully, is the force that overcomes and is equal and opposite to the friction. That's all you're doing. You can do that with one finger. All right, maybe, all right, 3 fingers. Right? Not hard. But to get that going at that constant velocity, you're not applying a force to the cart to get the cart moving. The cart has nothing to do with it. It's simply, solely, specifically, and only the friction between the wheel and the floor that you're pushing, that you're applying a force to overcome. True or false? Okay, now, that's what force is. Now, let's say that you're sitting in the chair. Do you feel yourself sitting in the chair? You feel your butt there sitting on that chair? You can feel that, right? Okay? Well, that's an acceleration due to gravity. That's actually your weight. Weight is mass times g, where g on Earth, small g, equals 10 meters per second squared. That's rounded from 9.8, right? Now, if I multiply your mass, my mass is 100 kilograms. So 10 meters per second squared, my weight in SI systems, my weight would be, don't go, yeah, walk this way, sorry, my apologies. My weight would be what? What's my weight? What's my weight? You can do this, nonverbal class. My weight is 1,000. What's that value? Kilogram meters per second squared. Kilograms times meters per second squared is kilogram meters per second squared. That's what weight is. Isn't that a little weird? Is that a little too much? Yes, it's a little too much. So what we say instead is, we call that a Newton. We say that that's equivalent to kilogram meters per second squared. By the way, I've already done all of this that I'm doing. This is completely, absolutely, positively, solely, and specifically a review. Okay, I've done all this. Yes? You get that? Okay, now. So I'm 1,000 newtons. That's my weight. What's the weight of this box? What's the weight of that box? Sabine, you know? What's the weight of that box? The mass is 1,000 kilograms. What's the weight of the box? T. 10,000 newtons. Now, if you take 10 of those boxes and pile them on each other, okay? What's the weight? What's the weight of all those boxes? What's the weight of all those boxes? 100,000. 100,000 newtons. Right? Isn't that the weight? What's the area that those are sitting on? What's the area?
1 meter squared.
You all right? Okay, what is it? 1 meter squared. So what's the pressure? What's the pressure? Give me the pressure. What is it? Want me to help you?
1 atmosphere.
No, I need to know the pressure, not what it's equivalent to, but I want to know the actual pressure. T. 100,000 newtons per 1 square meter. Isn't that correct? Yes or no? Right? There's something that I left out purposely. The definition of a Pascal. You know what the definition of a Pascal is? Anybody know? What is the definition of a Pascal? Yes?
Force over area.
Be more specific. 1 Pascal equals 1 Newton per meter squared. So, how many pascals is this? Isn't it going to be equal to 100,000 pascals, which equals 100 kilopascals? Yes or no? If I took a barometer, and I used water in the barometer, that's the height of the barometer. It's actually a little bit more than that. It's actually like up there. Okay? It's actually 101.3 kilopascals. It's a little bit more than this. This example is showing 100,000 pascals. That's close enough. It's actually 101.3. Sounds like a radio station in New York City. This is 101.3, bringing you the hits of the 60s, 70s, 80s, 90s, and the new millennium. No smiles. Alex is rocking back there, man. He's ready for the music to come on. I like it. I like it. You get it? So, can you imagine that's what you're under? Isn't that amazing? That's what you're under. You are under that enormous atmosphere. Can I erase this now? Okay? So, this is taking longer than I thought. What I'm going to do is, I'm going to quit soon and do this while no one's in the classroom. Oh no, I can do it next period, right? So I can continue next period, right? So let me just finish this idea. You ready for this? You really wanted me to like twist your brain around for a second? Okay? Here I am, 1,000 newtons, right? That's my weight, right? With this enormous atmosphere on top of me. Right? Right? There's enormous atmosphere on top of me, okay? Now, and I weigh 1,000 newtons. Yes? You okay with that? Now, I take that atmosphere away and I magically can breathe. It's magic, all right? Is the weight heavier, lighter, no different? You don't care. The atmosphere is gone. I'm on Earth without an atmosphere. Now I want you to think, what happens to this mass? Is it greater than 1,000 newtons or less than 1,000 newtons? No atmosphere. What's the answer? Anybody know?
Would it be less?
So I would weigh less than 1,000 newtons. So I have a vote right here, third row, less than 1,000 newtons. T. Same. All right, we didn't say same. Same. We have a same. Anybody else? Shall I give you a hint? Okay. Is air a fluid?
Yes.
Yes, okay. Therefore, air would have the same characteristics of any fluid, true or false? Therefore, it would have similar characteristics to water. Obviously, except for the density, because the definition of a fluid is anything that flows. Good. Now, You're at the shore. You're out at the Persian Gulf, wherever you go to the beach. All right? Right? You okay with that? Persian Gulf right out here. Very beautiful beach. Now, you see a rock in the water, right? That rock is pretty heavy. It's sandstone, but it's still at least heavy. What is it? It's heavy, right? You pick that up to look at it, and it's light, isn't it? Because it's in the fluid, right? It's called the buoyant force. Let me tell you what the buoyant force is. The buoyant force is the weight of the volume of fluid that the object displaces. The apparent weight of something in a fluid, in other words, what does it feel like? The rock doesn't feel as heavy, right, T? Doesn't feel very heavy? That's the apparent weight. That apparent weight is equal to apparent weight is the actual weight minus the buoyant force. When you're in water, how many people almost float? Raise your hand. Yeah. So, are you that heavy? If you were standing on a scale in the Persian Gulf, and you were standing on a scale that was all submerged, Z-Man is fed up, he's leaving. You're done? You quit? Oh, you're just getting something? Yeah. Excellent. So you stand on that scale. Is that scale going to read 1,000 newtons for me? No, it's not, is it? What does this enormous atmosphere do? Don't I have a buoyant force? Don't I? It's probably a half a kilo. Probably. Half a kilo times 10. It's probably about 5 newtons. So do I weigh less without the atmosphere or more without the atmosphere? Without the atmosphere, I weigh more. There's no buoyant force. You take that rock out of the water and put it on the beach and try to pick it up. What is it? What's the apparent weight now? The apparent weight is the weight. Cool, huh? Isn't that cool? I kind of sucked you into that, didn't I? Well, how did I suck you into that? I said, if you were under that box, you'd hear the bones crunch, and you all said yes. You did, didn't you? Right? If you have that rock under a mile of water, isn't it still light? Isn't it? Yes or no? Yeah, it's still light. What happens to your lungs, though, the rock is a rock, a rock is a rock. What happens to my lungs as I dive deeper into the ocean? Do they get smaller or larger? Smaller. They get smaller because the pressure is greater. If I take a balloon and I put it in water and I let it go, what happens? Right? Because the density of the balloon is much less than the density of the water, isn't it? But if I take that balloon and I submerge it into the water deep enough, what happens to its density? Eventually. It gets what? It gets less, it gets what? Greater than water, doesn't it? Because you're shrinking that volume. I'm shrinking the volume. As I shrink the volume, the density gets greater, doesn't it? Because the mass is the same, isn't it? Right? You get it or not? Are you okay with that? Shall we quit? So what's the actual, in other words, let's do one more thing and then we'll quit, okay? If I have a barometer, a mercury barometer, it looks like this. Okay, that's a eudometer. That's a tube that's closed at one end. You take the mercury and you fill the eudometer so it's full, right? You've done this with a glass of water in the sink, right? Right? You turn it upside down, and what happens to the water in the glass? It stays there, right? The column of water stays high, doesn't it? It doesn't go down, does it? Does it? Yes? So when is it going to start to go down? Well, it's going to start to go down as the column rises. It's only going to rise. How many meters is the column going to rise for a water barometer? How high? How high? 10.3 meters, right? Didn't I say that? This box, wasn't this box 10 meters? Wasn't it? Wasn't it? That water, that column of water, wasn't it 10 meters? Yes? Didn't I say it's going to be a little bit more than that? It's actually 10.3 meters. So you get a little more water up top. Cool, huh? Yes? But now, let's take this as Mercury. 1 atmosphere, Mercury. You ready? I take the eudometer, I put it in this giant vat of mercury, fill it up, put my finger in one end, I turn it like this, and I put it in here, and what happens? There's a very long tube, right? And it's filled with mercury, and it goes to right here, right? It only goes down that much. What's the height of that column of mercury? It's right on your test.
760.
Yes! Excellent! Australia is on the board. I like it. Like it. Ever been to Ayers Rock? Cool? Is it really cool?
I lived there.
What is it?
I lived there.
A little bit?
I said I lived in there.
Oh, you live near it? Excellent. Cool place? Excellent. I like that. $760 millimeters. Water, 10.3 meters. What's the density of mercury? This is curious. Density of water is equal to 1 gram per milliliter. Density of mercury is 13.6 grams per milliliter. You ready? That's 0.76 meters. Right? Yes or no? Yes? All right, now, very curious. Are you ready? Get out your calculators. Get out your calculators. You ready? Multiply 0.76 times the density. Multiply 0.76 times the density. What do you get? 10.3. Cool, huh? Isn't that cool? Isn't that cool? Cool or what? All right, I'm done. I'll do a second one and that'll finish it up.